Welcome to Differential Equations. This is section 1.1, and today we're just going to it's a short section, and we're just going to talk about some vocabulary and definitions. So we're going to start off with a bad pun. We've got deferential equations as opposed to differential equations. So those would be humble equations. And now I just want to assure you that you've been solving differential equations since you started taking calculus. Every time you integrate, you're solving a differential equation in a sense. So a differential equation is simply an equation that has a derivative in it. And we know to undo derivatives, we integrate. So for example, let's look at Newton's second law. Suppose Newton throws an apple up in the air. So I'm changing the story a little. So he's throwing it up, and h of t is the height of the apple from the ground at time t. And suppose the only force acting on the apple is acceleration due to gravity, then we're solving this differential equation. Force is mass times acceleration. So here's mass, here's acceleration, and force is mg. That's acceleration due to gravity. So the m's cancel, and I end up with the differential equation h double prime. So I'm switching notations here. H double prime is negative g. G is a constant, acceleration due to gravity. So to undo that second derivative and get to first derivative, I can integrate both sides, and that gives me h prime, that's the velocity, is negative gt plus some constant. I'll call it v naught for initial velocity. And then finally, to get the height, I can integrate again, and I'll pick up another constant. And so my point here is not, the details of this integration. It's just that in general, the solution to a differential equation is going to be a function. And that function is going to have some constants in it. Typically, every time you integrate, you'll pick up a constant. So a solution to a differential equation is not unique. And then to solve a differential equation, we do that by integrating. So this course is going to be about solving differential equations, but we're going to have to be a little bit more clever because we're not just going to be able to integrate functions in order to solve differential equations. If we could, then there wouldn't need to be a special course in solving differential equations. So let's talk about differential equations as models. We need to talk about proportionality. In mathematics, the way to translate the sentence A is proportional to B, that's not a sentence, actually, it's a phrase. A is proportional to B. The way we translate that is we write A is KB, and K is a constant. So for example, Jolene, my horse, her poop volume is proportional to the amount she eats. They're not equal. If I weigh the amount I feed her and I weigh her poop, they're not equal, but they're proportional, meaning the more I feed her, the more she's going to poop. The less I feed her, the less she's going to poop. So A is proportional to B. A can also be inversely proportional to B, in which case we write A is K over B. So an example of that would be Jolene's hunger is inversely proportional to the amount she eats. The more I feed her, the less hungry she is. And finally, rate always is derivative. So when we translate from English to math, when you see rate, you want to be thinking derivative. So let's do some simple examples. Write down a differential equation that describes the physical description. We're going to use K as our proportionality constant, and we want to use the variables given. We're not going to make up our own variables. The rate of decay in the mass A of bones with respect to time t. So that first phrase there, the rate of decay in the mass A with respect to t, all of that is dA dt, rate, dA dt. Now, it's not said that A is A of t, but that's implicit. A is a function of t. So dA dt is proportional to, so the way I write that is equals K, and then what is it proportional to? The mass at time t. Well, the mass at time t is A. So there is my mathematical sentence. dA dt is Ka. Let's do another one. The rate of decay in mass A of bones, so same thing with respect to time t, so that's dA dt, is proportional to, so equals K, the square of the mass at time t. Well, that's A squared. All right, the rate of change in the temperature, big T, of an object with respect to, that's WRT, with respect to time, is proportional to, so let's just start out with that part, the rate of change in temperature, so that's d big T, d little t, okay, because t is a function of time, is proportional to, so equals K, the difference in the temperature of the medium and the temperature of the object. Difference in math is subtraction, so I need parentheses. The temperature of the medium is Tm, and the temperature of the object, I'm told, is big T. So the difference is Tm minus T. That's Newton's law of cooling, and we'll solve that in the course. And finally, the rate of change of mass, A, in salt, so dA dt, is inversely proportional to, so this is K over, because it's inversely proportional to the square of the mass of salt present at time t. So that's A squared in the denominator. So notice the difference between B and D. One's inversely proportional, one's directly proportional. Classification, type, order, and linearity. So first of all, order. The order is the highest derivative that you see. So this is super easy. You just look at the differential equation. Here I see first derivative, so that's order 1. The next equation, I see second derivative. That's the highest derivative, so that's order 2. Now don't be fooled into thinking it's order 3. This right here, this is first derivative cubed. That's y prime cubed. That's different than y triple prime. Here's y double prime if I'm changing notations. So the highest derivative is 2. Type, there are ODEs and PDEs. This is a class in ODEs, so we will not see any PDEs in this class. PDEs are a dead giveaway because when you see a partial differential equation, you see that del sign. So those, well, we all took math, what is it, 2A, third semester calculus, so we know how to take partial derivatives. If you see a partial derivative sign, you have a partial differential equation. So we'll only see normal derivatives in this class, but let's just go through and determine the independent variables, the dependent variables, and the order. So I've got 2 ODEs and 1 PDE in my examples. The first example, the independent variables. Well, how can you tell? The independent variables are the ones in the denominator. So I'm taking the derivative of y with respect to x. That means y is a function of x. So x is independent, y is dependent, and the order is 3. Okay, next one. I'm taking the derivative of x with respect to t. That means t is independent, x depends on t, and the order is 1 because I see a first derivative. And the last example, my independents are t and x. That's what makes it a partial differential equation. It has more than one independent variable. Y depends on t and x, and a second order differential equation. Okay, finally, the most important definition for the purposes of this class is linear versus nonlinear, and we need to be able to recognize who's linear and who's not, because that's going to determine how we solve a differential equation. So rather than write out the whole definition, which is a little confusing, I thought I'd show you by example what's linear. A linear differential equation in y means the exponents of all the derivatives of y and of y are 1. So you're not allowed to square a derivative or take the square root of a derivative. And the only thing you can do to a derivative is multiply it by a function of x. No functions of y. So you can't take a y times a y prime. And then over here on the right-hand side, this function, for lack of a better term, I'm going to call it a driving function. It doesn't really have a name, but in harmonic motion, we call it a driving function. So I'll call it a driving function. It's only a function of x, not of y. So if you see the pattern here, the next one would be a sub 3 of x, a third order would be a sub 3 of x y triple prime plus a 2 of x, and then you multiply y double prime, and you go down to a naught of x, y equals big F. All right, so let's do a whole bunch of examples to determine who's linear and who's not. And in each case, we can determine the order of the differential equation, whether or not it's linear, because that's independent of linear or not. So the first guy, 2 y double prime. So my coefficients are 2 and then x squared times y prime. And then I've got e to the x times y. And then my driving function is 3x cubed. That's fine. That's yes, that's a perfect linear of order 2, because that's the highest derivative. Next one, it's looking good so far, and I'm changing up the notation here. I'm using Leibniz notation, but this in prime notation would be y double prime plus xy prime. So it's looking good so far. The left-hand side looks good, but unfortunately, over here, I have sine of x plus y. So there's my problem. That needs to be a function just of x, and it's a function of x and y. So no, that's not linear, but its order is 2. Okay, the next one, the problem with that, so this is not linear. Problem is I'm not allowed to multiply a y times a y prime. So this is not linear. It's got order 2. Okay, next one. It is linear. You're allowed to write things on different sides of the equal sign, but if I wanted to write it in the format at the top of the page, I'd write y prime plus cos x times y equals x cubed. So that's fine. The coefficients of the y and all the derivatives are 1 cos x, so those are functions of x, that's fine. And then my driving function is a function of x, so that's a linear differential equation. And that's got order 1. Next one, y prime plus y cubed is e to the x. That's a big no. You're not allowed to cube y. So that's no, but it's got order 1. All right. Next guy, same problem. Got second derivative plus, then I have first derivative raised to the 4th power. That's not allowed. That's a no. This has order 2. Next guy looks like y prime. So I'll write it in the format at the top of the page. It's 1 times y prime. 1 is a coefficient of x, so that's fine, a function of x. And then I have 0 y's, and that's equal to 3. So that's fine. 3 is a function of x, 0 is a function of x, 1 is a function of x. This is linear. Yes. So you're allowed to have missing terms. You don't have to have, in that definition, some of the coefficients can be 0, in which case you'll have missing terms. That's fine. They don't all have to appear. And this is first order. Next guy, I'm not going to multiply it all out, but I can see right away it's not linear because the dependent variable is p. When I distribute here, I'll get a p squared. So I'm supposed to circle the problem. The problem would be the p squared once I distribute. So that would be a no. And that has order 1. That's the logistic equation, by the way. And finally, here I'm changing up the variables. X is dependent, t is independent. And my function, so this looks like x double prime here, and this is a function of t. And then x prime, this is a function of t. X, 5t is a function of t. So this is good. This is linear, and it's got order 2. All right, so it's going to be a couple of lectures before we actually start solving differential equations. Just so you know that, don't get your hopes up too high. All right, and that's it.